Hello and welcome back for another video on power series. Now I have to warn you that this is probably the most difficult section in the entire course. So we're going to split this particular section into 3 different videos. What we want to talk about in this video are properties of power series. Specifically, how can we create new power series from existing power series by adding them or subtracting them, multiplying them, integrating them, or differentiating them. So we're going to split the video into 3 parts. We'll deal with addition and subtraction first. Then in the second video, we'll do multiplication by itself. It tends to be quite difficult. And then we'll look at integrating and differentiating in the last video on this section. So I hope that you have your control handy, because you may want to pause the video frequently in order to make sure that you're keeping up and understanding the algebra involved in representing new power series in terms of older ones. So let's go ahead and get started. I'll share my screen with you so you can see more closely exactly what the lecture notes look like. I have in this video written out some of the solutions to make it a little bit easier for you to follow. And then some of the solutions I'll write out in real time. Let's get started. So we want to start again by reviewing what we learned about power series in the previous section. Basically, a power series is a type of series where terms involve a variable other than the index of the series, so other than n or k. Typically, this variable is x. And if the variable is x, then the terms of the series involve powers of x or powers of the quantity x minus a, where a is some constant. So in this way, we can think of a power series as kind of being like an infinite polynomial. Now, if we do this, we can represent the polynomials as follows. So the first one is one that is a power series in terms of powers of just x. So we have the series from n equals 0 to infinity of x to the n, which is x to the 0 plus x to the first plus x squared and so on. But remember that we defined x to the 0, even when x is 0, to be 1, so that we could express all of these values, including at the center, which is 0. The second form is centered at a, and we have the expression x minus a being raised to the index power, which is n. And this, of course, gives us a series of terms with x minus a raised to a power. And again, we defined x minus a to the 0th power, even when x was a, to be the number 1. So this gives us c sub 0 plus c1 x minus a to the first plus c2 x minus a squared, and so on. So this is what we learned in the last section. Now, being able to create power series allows us to define new functions that cannot be written in terms of elementary functions. Now, what do we think of as elementary functions? This is probably a term you haven't heard before. Well, an elementary function is basically all the functions you've been dealing with over the past numerous years. So that would be your polynomials, your natural log, your exponentials, your radicals, your rational functions, trig functions, inverse trig functions, basically all the functions that you've learned about. Those are considered elementary functions. Well, there are functions that can't be written in terms of those, but we can use power series to represent them. It will also allow us, as we'll see today, to represent some of the transcendental functions like natural log instead in terms of these infinite polynomials. So we'll be able to represent a natural log instead as a power series where the terms simply consist of polynomial-like terms. So now let's go ahead and take a look at what it means to combine a power series through addition or subtraction. Now we're going to start with 2 known power series. So we have a power series here and a power series here. We need them to have the same interval of convergence. Now, if they don't have the same interval of convergence, then we look to see where they overlap. And we take that overlap as the new interval of convergence for both of them. Now, if they don't overlap at all, then we can't do this. We can't combine those power series in this way. So they have to have at least some overlapping region in their intervals of convergence. And then we can add or subtract the two original series to create a new power series defined on the overlapping parts of their intervals of convergence. And this is going to hold whether it's centered at 0 or at A. And again, we can let A be 0 or some other non-zero constant. So let's take a look now at example 1 and see how to apply this information. So we want to start with example 1, which is a more complicated example. And so I've written out the solution ahead of time. Remember to have your controller handy in case you need to pause the video. So when we're looking at this expression here, 1 over 1 minus x times the quantity x minus 2, this is a rational function. And we want to use the known power series 1 over 1 minus x, which again, we know what that is going to converge to, or we know what its power series representation is. This has a power series representation from 0 to infinity of x to the n. So this is the function, and this is its power series representation, provided that we're on the radius of convergence between -1 and 1, or interval of convergence, rather. The radius is 1. So we want to use that to construct a series for this rational function that we see here, and then we want to find the interval and radius of convergence for it. So this is something that we probably could have done in the previous section, but we want to start here to kind of get your feet wet and remind you of what we're doing. So the first thing that we're going to have to do with this rational function is it's got to be written somehow in the form of f of x. So a constant over 1 minus something involving the variable x. And we don't have that. We have two linear terms in the denominator. So instead, we use partial fractions to split up the rational function into the sum or difference of two rational expressions with simply linear denominators. So again, using the properties for partial fractions, this can be split into a over 1 minus x plus b over x minus 2. Now, since both of the factors are strictly linear, we can use the Heaviside method. So again, looking at the factor 1 minus x, it's 0. What causes it to be 0 is x equal 1. So we cover that one up and we substitute 1 in what's left of the rational function. And that gives us 1 over 1 minus 2, which is 1 over -1, which gives us -1. So in the numerator, over the linear factor 1 minus x, we put the -1. Then we repeat the process. This is the Heaviside method for partial fractions. We look at the factor x minus 2. Now its solution, or 0, would be the number 2. So then we cover up that factor and we substitute 2 into what's left of the rational function. And that gives us 1 over 1 minus 2, which again is 1 over -1, which is -1. So we replace the numerator over the linear factor x minus 2 with -1. So we have now broken down this rational function into the sum of two rational functions with simpler linear denominators. Now, we need to get these to match the format of f of x up here so that we can use the power series representation to rewrite these two rational functions. So what do we have? Well, we know we can deal with a constant by pulling the constant to the front. So I'm not worried about a constant in the numerator. However, I must have 1 minus something with a variable in it. The 1 in the denominator is not negotiable. One of these is already fine. The first one is in good shape. I've got -1 on top over 1 minus x. Simply pull the -1 in the numerator to the side and make it a constant coefficient. The second one, however, is not okay. I can reverse the order of the x minus 2 and write it as 2 minus x, and that would cancel the negative in the numerator, but that's a 2, not a 1. And I'm going to have to deal with that somehow. So again, what we're doing here is we're forcing the denominators to take on the form of 1 minus something with x. So we can use the power series representation for 1 over 1 minus x, which is the series x to the n, starting at n equals 0. So we rewrote the rational function like this, and then we can take the 2, and first I reverse the terms in the denominator. Instead of x minus 2, I get 2 minus x, but that would give me a negative on the outside. So let me write that down here. This is the same as negative 2 minus x. And then that negative and that negative will, of course, cancel. And that will give me 1 over 2 minus x. But it must be a 1. No other number will work. Must be a 1. So what we do now is we're going to have to divide this by 2. But I can't just divide one term in the denominator by 2. I've got to multiply by a form of 1. So I multiply by a form of 1 that looks like, on this term, 1/2 over 1/2. Now I can distribute across what's in the parentheses. And so this gives me 1/2 times 2, which gives me the 1 I was looking for, and 1/2 times negative x, which is negative x over 2. It also puts a 1/2 in the numerator. But again, we're allowed to do this. We're allowed to multiply by a form of 1 anytime we like, anywhere, any place, as much or as little as we prefer to do it. Now that we have written it as the form of 1 over or as something over 1 minus something with x, we need to rewrite it in the form that matches our basic power series, which is f of x equal 1 over 1 minus x. And again, this is going to be equal to the series from 0 to infinity of x to the n. So we want to use that. And again, the interval of convergence is from -1 to 1. This is our basic power series centered at 0. So we take the first fraction, which is this one here, -1 over 1 minus x. So what am I doing? I'm taking the representation I had here. I'm going to take each one of these one at a time, and I'm going to represent them with a power series. So first, I want to look at this term, -1 over 1 minus x. So I take the numerator to the front, make it a constant coefficient. That makes the numerator a 1, the denominator a 1 minus something with a variable x. Well, in essence, this 1 over 1 minus x is the function I have here, which is represented by the power series x to the n from n equals 0. So I can replace that with this, and it still has the -1 multiplied by it on the outside. And again, the interval of convergence is going to be between -1 and 1, because it's essentially a geometric series in form. Now let's look at the second term that came from the original rational function here. So we just dealt with that term and represented it with a new power series. And now we want to take this term, we want to do the same thing, represent it with a new power series. So when we represent the second one, we need to pull the 1/2 to the front, and that gives us 1 over 1 minus something with x. So 1/2 remains a constant coefficient. And then we use the form that we see here, f of x is 1 over 1 minus x, and we do a substitution of x divided by 2 in place of x, which gives us the power series 1/2 times the series x over 2 to the n. Now this is going to be true provided that x over 2 is between -1 and 1, which basically means that the magnitude of x is less than 2. So between -2 and 2. Now this is two different intervals of convergence. So if I'm looking at this one up here, I've got an interval of convergence between -1 and 1. but this one has an interval of convergence between -2 and 2. But again, we have to take what overlaps. So what do they have in common? Well, -2 to 2 is a wider interval, and -1 to 1 fits inside of it. If you want to look at these on the number line, you can look at them here. So there's 0, 1, 2, -1, -2. So 0 to -1 to 1 fits here, and -2 to 2 fits here. So what they have in common is between -1 and 1. So the interval of convergence for the combined power series will have to be that overlap -1 to 1. That will make it work for both series. So we've taken this rational expression, we split it up using partial fractions, and then we converted each one into 2 power series. Now I've reversed the order here because this one had a -1 on the outside, so I wrote it at the back, but this one ended up being positive, so I wrote it at the front. So in case you're wondering why they don't match the order that I worked them in. So this is basically what we've done here. Now, could we represent this a slightly different way? Yes, we can. The 1/2, I mean, this is in essence a power series, and we know that they both converge over the interval of convergence -1 to 1. We can pull the 1/2 inside because we know it converges. We're allowed to do that on convergent series. So this gives me 1/2 times 1/2 to the n. Notice I split apart the x and the 1/2. So you can think of this x over 2 as 1/2 times x. And I split them apart and raised them both to the nth power because they're both in parentheses with the nth power outside. That gives me another 1/2 factor, which gives me 1/2 to the n plus 1, or since 1 to a finite power is 1, that gives me 1/2 to the n plus 1. So let me scroll up so you can see that part. So I ended up with 1/2 to the n plus 1. Now, I also have this x to the n here, but this series is also x to the n. And I know these are convergent series on the interval of convergence. So there is a rule, a property of series that says if they converge, then you can pull them into one series. So we can combine the 2 series together. And if you want to write it out longhand over here, this gives you the series from n equals 0 to infinity. And I should probably write 1/2 to the n plus 1 times x to the n minus, oops, somehow that became a 2. I don't know how that happened. X to the n minus x to the n. And all of this is inside one series. And we could do this because we know they converge on the radius of, or interval of convergence. Now this makes x to the n a common factor in those 2 terms of the summand, so we can factor it out. And you can get this as your final form. So basically, we've represented this rational function as this infinite polynomial over the interval of convergence from -1 to 1. So we've created a new power series for a rational function by writing it as the sum or difference of 2 power series that we know converge. And because we know they converge, we're allowed to push them together into one power series. Let's now take a look at the theorem that deals with adding and subtracting power series that are known to converge on some interval of convergence. So we start with the supposition that we have a power series, c to the n, x to the n, and we have another power series, d sub n, x to the n. So it's just 2 different power series, whatever they are. And suppose they converge to the functions f and g. So for example, this first one could just be x to the n, so it converges to 1/1 minus x. We know that. And this could be a different one. that converges to some other function. And we did some of this in the previous section. So we have two power series that converge to two functions on their own intervals of convergence. Now, let's suppose that they have a common or overlapping interval in their intervals of convergence. We're going to take that overlap as the new interval of convergence. Then we can say that when we add the two power series together or subtract them, it will converge. And in fact, weirdly, it converges to f plus or minus g. So if you add their power series representations together, you would get the same function as if you took the function forms of f and g and added those together. And the same for subtraction. Now, this is pretty powerful. This gives us ways of building new power series for different functions based on ones we already know converge on some interval of convergence. Now, the next two parts of this are somewhat more complicated. So they look terrible, but they're really not that bad. We should really probably call this section adding, subtracting, and composition, but at any rate, or even multiple by a factor. So what we've got in this next case is if we take any integer, so the negative whole numbers, positive whole numbers, and zero. So -3, -2, -1, 0, 1, 2, 3, 4, 5, going in both directions. That's an integer. In this case, we want m to be greater than 0. If we do that and we take any real number b, all right, so b is just a constant, then the power series multiplying b x to the m times our known convergent series, c sub n x to the n, then because this x to the m, as in Mary, does not depend on the subscript n, the index of summation, we can pull it inside. We know that this one converges, so I'm allowed to pull constants in and out. If we don't know it converges, we're not allowed to do that. But it does converge, so we're allowed to pull those on the inside. Well, then b and c sub n are constants, so I can multiply the constants together. And then I can take the two factors that depend on x to the m as in Mary, and x to the n as in Nancy. And since the bases are both x, I add the powers. So this gives me a factor x to the m plus n. Now, here's the wild thing. We know that this will also converge. And again, we're assuming that we've got some whole number basically here, and we've got some real value right here, b. We know that it will converge to that same constant b, x to the mth power, m as in Mary, multiplied by the function that the original power series converges to. So we can multiply a known power series by a power of x to a known power, and by some constant, and it will still converge, and it will converge to that constant and that power of x multiplied by the function, and it will still be on the interval of convergence. So it doesn't even change the interval of convergence, which is crazy. See, that's pretty powerful, all right? So we can create these new functions and new power series from old ones. Let's take a look at the next one. The next one is more composition. You're placing an expression inside of another expression. So in this next one, we're taking our convergent series, which is c sub n x to the n, which we know converges to f. We're told that in the beginning. We assume that. And we're replacing the x with b times x to the m. So again, b is some real number and m is some non-negative integer. So basically a whole number. So if we take this and we put this in here, in fact, it works even if it's not, then we know that this is going to also converge. So remember here that we take b to the nth power, so that comes out as a constant multiplied by c sub n, and then x to the mth power to the nth power 1 base x, 2 powers, m as in Mary, n as in Nancy, multiply the powers together, gives you x to the m times n power. Now here's the wild thing. According to this theorem, that also converges, and in fact, it converges to the original function f composed with that b x to the mth power. So it will converge to this with one caveat. This b x to the mth has to be in I. So this could change our interval of convergence. So we take the magnitude of bx to the mth and we set it less than equal to whatever our interval of convergence or radius of convergence is. So bx to the m will have to be an I. Now I said that this looks really complicated, and it does look really complicated. It's not that bad. It's bad, but it's doable. Let's see how to apply this. Now, we also have the same situation for functions that are centered at x minus a. So we can go through and make the same theorem apply to all power series that are centered at a. So where the base of the exponential part is x minus a instead of just x. And again, the conclusions are the same, all right? So again, we have this situation applying whether it's centered at 0 or some non-zero value a. Let's take a look now at how to apply it in example 2. So what does example 2 say? It says, suppose the series c sub n x to the n starting at n equals 0 has an interval of convergence from -1 to 1. It doesn't tell you what it converges to. It just says it does converge, and that's the interval of convergence. What is the interval of convergence of the power series with the same constant coefficient c sub n, but with x divided by 2 replacing the x in the original power series? Well, this is like a composition, right? You're substituting x over 2 in place of x. So let's go back to the theorem and see what it said about this situation. So let me find my cursor so I can get back up to the power series. This is the third situation, which you'll see right here. In this particular case, we're substituting some new expression in terms of x into the original power series, and it will converge provided that bx to the m is in I. So how do we apply this when we look at example 2? So basically what this means, the original up here has a series interval of convergence between -1 and 1, which means that the magnitude of x is less than 1. The new series is substituting x over 2 in place of x. So the new series will converge provided that x over 2 replaces that in the original interval of convergence. So this x over 2 still has to be an I. But that's going to give us a slightly different interval of convergence for this new power series. But again, x over 2 would be in I, provided that the following is true. So we can pull the 1/2 out of the absolute value, and then we can multiply both sides by 2, and that gives us the magnitude of x is less than 2, which basically tells us that the new power series has a radius of convergence equal to 2 and an interval of convergence equal to -2 to 2. So, and again, we don't need to check the endpoints because we got this from the theorem. It says it will converge and will converge to whatever you get when you substitute what was substituted into the power series into the original limitation on x. And so we end up with this power series here, the new one, converging as long as x is between -2 and 2. All right, let's take a look now at the next example, which is example number 3. When we're looking at example 3, it says, use the power series for f of x equal to 1 over 1 minus x, again on the interval of convergence from -1 to 1, to find the interval and radius of convergence of a new power series from 0 of x to the 3n divided by 6, then express it as a rational function. Okay, well, we're told that this must converge, so I've got some things that I can do to it because I'm looking for the interval and radius of convergence. But the first thing I want to do is I want to write this in a format that looks like the original with maybe a constant multiple on it or something substituted in place of the original x. So remember that this one is, again, the series from 0 to infinity of x to the n. That's our basic power series centered at 0. So I want to get this written as close to this as I possibly can. So what I do is I take my original, n equals 0 to infinity, x to the 3n power divided by 6, and I rewrite it so that the divided by 6 becomes the 1/6 constant coefficient times. And then I've got to get the n and the 3 apart, right? This has something to the nth power. So I need something to the nth power. Well, those powers are multiplied together. So that means that I could write it as x cubed to the nth power. Now, what am I doing? Well, this 1/6 is like that constant b that's being multiplied by the original power series. And this x to the third is like the third case where you're substituting something in. So if we have this situation, then by the theorem, we should have convergence. It should converge, and I'm going to write it out in words, to 1/6. This will be multiplied by the original function f, and inside f, we want to substitute x cubed in place of x. So I'm taking the constant that was multiplied by it, and I'm multiplying that by the function expression, and I'm taking the x to the third, which is replacing x, and I'm substituting that into x cubed. So if we go back to our original theorem up here, this is basically a combination of parts 2 and part 3, where from part 2, we're just taking the constant b, and from part 3, we're substituting x cubed in place of x. So now let's see what we should do next. So I know that I've got this expression here, but I know what f of x is. So I can rewrite this power series that I've got here in terms of a rational function. So my rational function is going to be 1/6 times 1 over 1 minus x cubed. And then, of course, you should distribute the 6 across the denominator, which gives us 1 over 6 minus 6x cubed. Now, I've kind of done this in reverse order. It said to express it as a rational function last, and I actually did that first, but anyway, it's all good. Remember that multiplying by a constant does not change the interval of convergence at all. It stays the same. So multiplying by 1/6 does not change I. Substituting something in place of x can change I. So it will converge provided that this x cubed is in the original interval of convergence, which is magnitude less than 1. So this is going to converge on the interval of convergence given by the following. Given by the magnitude of x cubed less than 1. Now, the next thing that we can do, of course, is we can take the cube root of both sides. Remember that cube roots maintain sign. So if it's negative, it'll stay negative. If it's positive, it'll stay positive. So this leads to the magnitude of x being less than 1. Well, that was the original interval of convergence. So in this case, unlike the previous example, in this case, what we substituted in place of x did not change the interval of convergence. So in this case, we have a new function, 1 over 6 minus 6x cubed, represented by this power series, x to the 3n over 6, and it applies on the interval of convergence between -1 and 1. This is how we apply the theorem to create new power series and new function representations from old ones. Let's look at another example, which is example 4. So example 4 wants us to find the interval and radius of convergence, or at least the interval of convergence, for the power series x to the n over 3 to the n starting at n equals 0. Now, we're going to start with the basic power series, which again is the series x to the n starting at n equals 0, which gives us the function 1 over 1 minus x. Remember, we got this because it's basically a geometric series, and this is a first over 1 minus r, where the common ratio is x. So we're going to take this pattern, and we're going to try to make this fit the pattern. So we're going to see if maybe we're adding two different ones together, which doesn't seem likely in this case, or whether we're multiplying by a constant or some power of x, like x cubed, which also doesn't seem likely in this case, or if we're instead substituting something in place of x in the original power series, which seems likely in this case. So what we want to do is take this one and see if we can write it in this form. So we're going to get it as close as we can. So we're starting with the series n equals 0 to infinity. And I'm going to write it as x to the nth power over 3 to the nth power. Now they're both being raised to the nth power. If they weren't, I would break off one or two of whichever one I needed to until the powers match. Once the powers match, then I can take those bases and divide them and put them in parentheses with the power on the outside. So now this becomes the series starting at n equals 0 of x cubed, or x over 3, the quantity raised to the n. I've got x cubed on my mind now from the last one. Now, that looks like the third situation of the theorem. And the theorem says that if you're substituting, composing, you're substituting something in place of the x in the original power series, it will converge, and it will do it on an interval of convergence as long as whatever you substituted is inside the original function's interval of convergence, which is this guy. And this guy has an interval of convergence, a restriction given by the magnitude of x less than 1. So coming over here, all we need to do is take the magnitude of x over 3, replace x with that, and set that less than 1. Now again, the absolute value is 3, so you can split this as 1/3 times the absolute value of x less than 1, multiply both sides by 3. The 3 is positive, so you don't need to reverse the inequality, which basically tells us that x is between 3 and -3. So this gives us an interval of convergence from -3 to 3, and the radius of convergence, of course, is half the width of the interval, which is 3. Right? So hopefully this is making more sense to you and you're feeling a little bit more confident about it now. It's really not that difficult to apply the theorem. Remember that the first two parts of the theorem do not change the interval of convergence. You're just looking for where they overlap. The third one can change the interval of convergence. The third one, we have to make sure that whatever we substituted in place of x fits the original interval of convergence. So I believe that was example 4. So now we're ready for example number 5. Now, when we're looking at example 5, this one is actually more difficult. It's a harder problem because we have a more difficult representation. Let's see what happens. So let's take a look at what example 5 is asking us to do. It says express the series from n equal 1 this time, not 0, of 1 over x to the 2n power as a rational function. Then find the interval of convergence I. We can also maybe find the radius of convergence. Here's a hint. The series starts at n equal 1. Since this series starts at n equal 1, then we want to look at the series where x to the n, the basic power series, also starts at 1. But if this starts at 1, I've changed the value of a first. So a first is no longer a 1. A first is something different. In fact, it's x. So this is going to converge to something other than 1 over 1 minus x. We need to find that function that it converges to first. So from a first over 1 minus r, the first thing we want to do is represent what this looks like. Now, if you need to, go ahead and write out some of the terms. You have x to the first plus x squared plus x cubed plus x to the fourth plus dot, dot, dot. We can see that in this case, the first term in the sequencer series is x to the first, or just x. It does still have a common ratio. To get from one term to the next, we still multiply by x. So r is still equal to x. So we can use the formula for a convergent geometric series, a first over 1 minus r, to say that this must converge to x over 1 minus x. So this is our new function, f of x. So this is going to be something different. So this is not the original. So maybe I shouldn't call this f, I'll call this g. Right? So this is a different function that the series converges to when it starts at 1. So you do need to make sure that you're comparing to the same type of series. So you want to generally have them starting at the same lower index of summation. Okay, so now I need to take this original series that we have here from n equal 1 of 1 over x to the 2n power and represent it in terms of the basic series from n equal 1 of x to the n. So I'm going to go ahead and start, and I'm going to take my series n equal 1 to infinity of 1 over x to the 2n, and I'm going to rewrite this as the series n equal 1 to infinity of x to the negative 2n. Remember that when you change from the denominator to numerator or vice versa, it changes the sign of the exponent. So now we have a negative 2 power. So what I'm going to do here, and again, that theorem, I have it written in integer greater than equal to 0. That's not actually the case. It's just an integer. Any integer will work. I'll need to fix my notes. So now we're going to represent this as the series from n equal 1 to infinity, and I'm going to pull the power negative 2 away from the power n. Remember, when you have one base and two powers, you multiply the powers. So these two are equivalent to each other. Well, now I have it written in the same format as my basic series, starting at 1 of x to the n. And I know that it converges to x over 1 minus x, which we call g. That means that this series, which is essentially the same, but with x to the negative 2 substituted in place of the x, is going to converge to g of x to the negative 2. So this converges to g of x to the negative 2, which is going to be x to the negative 2 over 1 minus x to the negative 2. Now, if we're looking at this and we want to work this out and get rid of those negative exponents, which we definitely want to do, we may want to re-represent this without the negative exponents. In other words, drop those to their denominators and change the power to positive 2. So this g of x to the negative 2 can be thought of as g of 1 over x squared, which becomes 1 over x squared over 1 minus 1 over x squared. Now that's a complex fraction, which we don't like to leave. So what we're going to do instead is we're going to multiply by a form of 1 of x squared over x squared. And you can make it match the complex form if you want to. Keep track of the top and the bottom of the top and so forth. And when you distribute this, because you do need to distribute it across the denominator where you have two terms, you end up with 1 over x squared minus 1. So our new power series, which is this one up here, is going to converge to g of x to the negative 2, which gives us the new function 1 over x squared minus 1. Now we know that composition, substituting something in place of x, can change the interval of convergence. Doesn't have to, but it can. So we want to see if this changes the interval of convergence. So we come back up here and we ask ourselves, what is the interval of convergence for this power series that we have at the beginning, the basic one? And of course, it converges for the magnitude of x less than 1, because that is the condition for convergence of a geometric series. So this will converge on the following interval, provided that the magnitude of what we substituted in place of x, which was 1 over x squared, also fits within that original interval of convergence. So the magnitude of 1 over x squared has to be less than 1. It's got to be between negative 1 and 1. Now, this is going to be kind of weird, but again, something that's squared is definitely non-negative, and the 1 is non-negative, so we can drop the absolute values, and this gives me 1 over x squared less than 1. Again, this is assuming, of course, that x is not 0. And then I can multiply both sides by x squared, which is definitely positive, so I don't reverse the sense of the inequality. And this leads to 1 less than x squared. Now, when I take the absolute value of this thing, I'm going to get something a little bit different. So when I take the absolute value, this is going back to algebra, or when I take the square root, I get an absolute value. So when you take the square root of both sides, you're going to get 1 less than the magnitude of x. There are two possibilities. The absolute value of x is bigger than 1. So the magnitude of x is bigger than 1. So a number like 5 would work, that's bigger than 1. But a number like negative 5 also works because the magnitude of negative 5 is 5, and 5 is bigger than 1. So this splits into two situations. Either 1 is truly less than x, or negative 1 is greater than x. In other words, x is below negative 1. So it's either 1 and up or negative 1 and down. Those would give you numbers whose magnitudes are bigger than 1. So once we look at this, what's happened to our interval of convergence? If we look at these and we plot these on the number line, plotted on the number line, here's 0, here's 1, here's negative 1. This is going to be negative 1 to the left. That's the second one. And then the first one becomes 1 to the right. In other words, for 1 over x squared to be less than 1, fit in the original interval of convergence, then the magnitude of x has to be bigger than 1, which means that it either falls from negative infinity up to -1 or from 1 to infinity. So our interval of convergence is a combined region from negative infinity up to -1, union 1 to infinity. And because those are both infinite subintervals, then we would say the radius of convergence is infinity because they are essentially infinitely wide, right? So I hope this sort of makes sense to you what we did here. The algebra is rather complicated, especially here when we're dealing with the inequality. If you need to review, go and review inequalities with absolute values, and you'll see that this is the case. All right, we have one more example to work in this section, which is again a more difficult example. So what I've done is I've written out the solutions for you. And what we're going to do is we're just going to go through it. All right. So in example 6, we want to express the series as a rational function again and find the interval of convergence I. Now, this one is starting at n equal 1. So you have a choice to make here. You could do what we did in the previous one, which is compare it to the power series from n equal 1 to infinity of x to the n, which converges to x over 1 minus x, or you can change the index of summation starting at 1 to 1 starting at 0. Either one is fine, but it will change the power series and the function you're comparing it to. So you need to be careful when you do this and make a choice. I prefer to go to n equals 0 because then I know that it's based on the basic geometric series x to the n, which converges to 1 over 1 minus x. This function has a simpler form than x over 1 minus x. So I like to use this one better. But if you want, you can do this one as well, and you could convert it and compare it to the series from n equal 1 to infinity of x to the n, which converges to x over 1 minus x. Also, when the magnitude of x is less than 1. They both have the same interval of convergence because they're both geometric series. So you can compare it to either one, choose your method. I decided to move it back to n equals 0 so that I could have 1 in the numerator and not x. Because these looked complicated enough, I was afraid it would get really complicated if I tried to use this form. And in fact, it probably does. I haven't tried it, but my guess is the algebra gets pretty nasty. So I moved it back to 0. And that means that I am going to take this one right here, and I've got to move it backwards. So we're going to split it into a series. And right here is where I did it. All right. So I'm told that it converges. And because it converges, I can split it into 2 series, right? So I'm told that it converges. I'm looking for the power series that represents it, or rather not the power series, the function that represents it. I already have the power series, although I'd like a better form for the power series. That's a better way of putting it. So I split it into 2, and then I rewrote it starting at n equals 0. So to rewrite it, I'm going to have to back the lower index of summation up by 1, subtract 1 here. So to compensate, I have to replace all the n's with n plus 1. I have to add 1 to compensate. So when I do that, you can see that work over here on the right. So when I made this start at 0, my n's became n plus 1s. All right, and then I look at the power. 2 times quantity n plus 1 minus 1 gives me 2n plus 2 minus 1, which of course, if I work out 2n plus 2 minus 1, I get 2n plus 1, which becomes the new power on each of these expressions involving x. So I've got the 2 expressions here. Okay, now I need to be able to represent it in this format. which means I need one thing dependent on x to the nth power. And I've got the n2n plus 1 power. I can deal with the 2 by separating the 2 and the n, but I've got to deal with this plus 1. So I remove the plus 1 by writing it as x minus 3 times the quantity x minus 3 to the 2n, and doing the same thing for this expression here. So that changes the power from 2n plus 1 to 2n. Now I can go ahead and rewrite these again. So I'll leave that there so you can see the work that's done. So I took the x minus 3 in the denominator and moved it to the numerator by raising it to the negative 1 power. I took the x minus 3 to the 2n power and raised it to the numerator by taking it to the negative 2n power. And I did the same thing on the second series with the base x minus 2. So essentially they're doing exactly the same thing, just the bases are different. Now, I separate the negative 2 from the n so I can get something raised to the nth power. So I have this x minus 3 to the negative 1 times x minus 3 to the negative 2, all raised to the nth power. Now it matches the form that I was looking for in the original, right? So I'm looking for this form right here, the sum from 0 to infinity of x to the n, which I know converges to 1 over 1 minus x when the magnitude is less than 1. This is the one that essentially we end up having it memorized because we use it so often. This must converge by the theorem to the following. This is an expression involving x multiplied by our power series, which does not change the interval of convergence. This, however, where we're substituting x minus 3 to the negative 2 in place of the x, that does or can change the interval of convergence. So it must converge, and it must converge to x minus 3 to the negative 1 times the function with x minus 3 to the negative 2 in place of x. So we rewrite this. This is x minus 3 to the negative 1 times 1 over 1 minus what replaces x. Now we can rewrite it without negative exponents, and we get this expression here. We can distribute the quantity x minus 3 over the two terms in the second fraction, and that will give us 1 over the quantity x minus 3 minus 1 over x minus 3. So I still have a complex fraction because I have a denominator in my denominator. So I multiply by 1 in the form of x minus 3 over itself, which gives me x minus 3 over x minus 3 squared minus 1. Now, this must converge provided that this thing that I substituted in place of x is less than 1. You'll notice I didn't include the magnitudes because it's squared. So if that's bothering you, go ahead and put the absolute values in, all right? That it's fine, but it's squared, so it's strictly non-negative to start with. So what possible effect did that have on our interval of convergence? So let's take a look. So I rewrite the x minus 3 to the negative 2 as 1 over x minus 3 squared. It is squared, so I drop the absolute values. It's got to be less than 1. Assuming I can multiply both sides by the denominator, it's strictly positive. So it doesn't reverse the inequality. So I get 1 less than x minus 3 quantity squared. When I take the square root of both sides, I get the magnitude of x minus 3 is greater than 1, which means that it really is bigger than 1, or it's less than negative 1. So it's either at 1 and out or negative 1 and down. But that's x minus 3. So where would x be? Well, to find where x would be, we add 3 to both sides of the inequality, and we get that x is greater than 4, or adding 3 to both sides of this inequality, we get that x is less than 2, right? So this gives us this interval right here from negative infinity to 2, together with the interval from 4 to infinity. All right, so that's what our interval of convergence looks like for that particular power series. And this is what it looks like on the number line. So from open 2 to the left, open 4 to the right. Now we have to repeat this entire process on the other power series part, which is this one right here. So we repeat all the steps that we did right there. And it essentially follows the same path. All right, so we rewrite x minus 2 to the negative 1. We know it's got to converge to that factor multiplied by the function with x minus 2 to the negative 2 replacing x. Rewrite it without the negative exponents. Go ahead and multiply through by the factor x minus 2. That gives you 1 over x minus 2 minus 1 over x minus 2 multiplied by 1. That gives you x minus 2 over x minus 2 quantity squared minus 1. Very similar to the previous one. In fact, it's exactly the same, just with x minus 2, not x minus 3. Again, our condition for convergence is that the thing we substituted in place of the x, the composition, has to be less than 1, the original interval of convergence. So again, we go through and we represent that by rewriting x minus 2 to the negative 2 as 1 over x minus 2 squared, multiply both sides by that, take the square root, which gives us absolute value on the right, which means that 1 is less than x minus 2 or negative 1 is greater than x minus 2. So either 1 and up or negative 1 and down. And then to find where x is to make that happen, we add 2 to both parts of the inequality, and we get x is greater than 3. Or in the second case, we get that 1 is greater than x. So we have these two inequalities, and they are an OR because this is a split situation. It's not a combined inequality. It's not an AND, it's an OR. So we have negative infinity to 1, union 3 to infinity, which looks like this one. So from open circle at 1 to the left, open circle at 3 to the right. So we have these two power series being subtracted together, and they have different intervals of convergence. So what we have to find is where they overlap in order to find where this combined power series is going to converge. There's got to be some overlap in these intervals of convergence. So I thought the easiest thing to do would be to put them all on the same number line. So I put the two intervals of convergence on the same number line. And now you can see by looking at it what they have in common. So from open 1 to the left, which is negative infinity to 1, and from open 4 to the right, that's the region that they both include. So that becomes our new interval of convergence for the combined power series for these two. Now, what does it converge to? What's the function? What's the rational expression? What converges to g of x equal to x minus 3 over x minus 3 quantity squared minus 1 minus x minus 2 over x minus 2 quantity squared minus 1, and again over that interval of convergence. Now, could you get a common denominator? Yes, but it would be ugly and it would be nasty. And it probably wouldn't be as clear what the structure of it is as it is in this format. So we want to leave it in this format because this is probably the best format for showing the underlying structure of what this rational function looks like. So this is the last example that we wanted to do in this section, which was adding and subtracting, also multiplying by constants and doing some composition in order to take old power series and create new power series that converge to particular functions on their interval of convergence. In the next video, we want to take a look at multiplying power series that are known to converge on some overlapping interval of convergence and see how we can define the new power series and the new function that results from multiplying them. I hope you'll join me for that section.